Hi everyone, welcome back to the channel. In this video, we will going to learn about the NAND gate and how it works as a universal gate. I will be going to show you how the implementation of other 6 gates other than the NAND gate. So with the help of NAND gate, how we can implement the other gates as well. So that includes AND, OR, NOT, NOR, XOR and XNOR gates. For XOR and XNOR gates, I will be even made 2 different circuits each because they can be built in more than one way using NAND gates. So this is a full and clear explanation of how NAND alone can help us design all basic gates. So let's get started and understand the power of NAND gate. The 3 gates has been completed. So I hope you understood those 3 gates. So let's start the universal gates. So in universal gates we have only 2 gates, that is NAND gate and NOR gate. So with these 2 we can perform any of the operation that can be performed with the normal gates also. So these things, so NAND gate implementation as a universal gate will be going to see in the upcoming video. So in this video just we are going to discuss the truth table and its output equation. So if you observe there, that is the symbol. So the AND gate is just added with the NOT gate, that's it. So it is the next, that is the output equation. If you observe, so y is equals to a dot b, so and whole bar. So we have a dot b, we already saw in the AND gate. So the NOT gate is also added, so that we have to add the bar also. This is the NAND gate. In this video only we are also going to discuss the full diagram or the full circuit of the NAND gate. So if you observe there, so we have given with the equation that is y is equals to a dot b whole bar. So a dot b, that is AND gate, so bar is there, that is NOT gate, inverter. So inverter of a dot b. So we are going to place the NOT gate, the input as a dot b, output as a dot b whole bar, as you're seeing there. So this is the expression or expansion of the NAND gate. So if you observe the truth table of the NAND gate, so that is if both are ones, that is 0, if both are zeros, that is 1, and remaining 2 cases it is 1. So why this truth table is like this? So if you see the truth table of the AND gate, so if it's just opposite of the truth table of the AND gate, so that is NAND gate. So because in AND gate we are going to have a dot b, but in this case we just added NOT gate. So output also just flipped. NAND gate is just flip of AND gate. There are 2 universal gates. So first one is NAND gate and second one is NOR gate. So in this video we are going to see only the NAND gate implementation. So NOR gate implementation will be seen in the upcoming videos. At first we are going to see about the NAND gate implementation about these 3 gates. Then how the NAND gate can be implemented with another universal gate as well. So we are going to implement NAND gate to form or to build the NOR gate as well, the another universal gate. At last we are going to see the implementation of NAND with these 2 gates as well, that is XOR and XNOR. Individual XOR and XNOR we have separately two implementations because this is a complete circuit. So it's a shortcut symbol, so we have big circuit for XOR and XNOR. So we are going to see 2 implementations for each of XOR and XNOR using NAND gate. This is the overall view of all gates that have present, that is 7 gates. So first let's start with the first 3 basic gates. So let's start with the easy one. So if you consider the NOT gate, so if your input is A and output will be just inverted, so that is known as NOT gate. So A comes, A bar out. So the NAND gate, as we saw in the previous slides, that is A dot B whole bar, that we are going to see with the help of NAND gate also. So NAND gate can be converted to NOT gate. How? So if the input, we have 2 inputs, so that is 2 inputs. So in the 2 inputs we have to take the same input so that we can be able to invert the input. So if you observe, I am taking 2 A's. So 2 A's means in Boolean algebra that A into A whole bar means A only. If 0 into 0 means 0 only. 1 into 1 means 1 only. So we are going to take one variable. So if A comes, A bar goes. That's the final motto. It is NOT gate. Simply we can also represent by merging both of those 2 inputs and simple A input with the A output as A bar. So whatever may be the logic inside that, so if the same logic can be produced with the NAND gate, so that is why it is known as the universal gate. So if you observe NOT gate, A is coming, A bar is going, whatever may be the inside circuit. So the NAND gate can also be done like that only. A is coming, A bar is going. That's the same logic, so that we are implementing NAND gate with NOT gate. So that is the representation. So next one we are going to see is that AND gate. So we have know that AND gate means A dot B. NAND gate means A dot B whole bar. Just the NOT gate is added. So in the circuit also we are going to just add the NOT gate. So up to now we already saw the NOT gate implementation using NAND gate. So simply we are going to add NOT gate so that it becomes the NAND gate. So let's see. So the logic you can see there. So A and B is coming, A dot B is going out. So that is the same logic that we have in AND gate. So that is why we are calling that AND gate can be implemented using NAND gate. So we have to have two NAND gates to represent AND gate, because the output of first NAND gate is A dot B whole bar. So that whole bar has to be replaced with normal A dot B, so that we have to have inverter. So for inverter we have already saw the implementation, same output that can be inverted. So that's the logic gate for the AND gate using NAND gate. As you can see in the green highlighted way boxes also. So that boxes corresponding, so whatever may be the inside NAND gates, how many may be the inside NAND gates, but the same logic we have to produce that AND gate is producing. So that's the way. So that is why we are calling that AND gate can be implemented using NAND gate. For each gate we have separate different NAND gate circuits. So different NAND gate circuits represents the different logic circuits. This circuit is main. So why we are doing all these things? Because for this circuit only we are doing all these things for finding this the circuit diagram only. So we are trying to find the equation. From the equation only we are going to see the output, and the output we are going to draw the final NAND gate circuit. So the required one is very important, and the formula of the NAND gate is very important for doing like this. In the basic gates we are going to see the final thing, that is OR gate. So for the OR gate, so first we have to analyze the formula of the OR gate, so that after analyzing the formula we are going to justify with the NAND gate output formula as well. The output equation for the OR gate is A plus B. We have to add double bar. So by adding double bar, it's not a big change. It's not a change. We can, because both of the bars can be cutted out easily. So according to the Boolean equations or the Boolean formulas, we can split dot with plus with dot, and bars can be splitted to the individuals. So the Boolean formula I have applied there to the inner bar, so that it becomes like that. As you seeing there, so that is so we have to take two inputs for the NAND gate. So first one is A bar, second input is B bar, and finally we are going to get output as A plus B. How? So I have back traced. So A plus B, I have first applied bars, so I have took a formula, that is A bar dot B bar whole bar. So if you observe clearly, that is A plus B only. So that is the thing we are going to apply. So if you clearly observe, that is the NAND gate. So A bar is one input, B bar is one input, and we have A dot B, means suppose if you take, that is A bar as X and B bar as Y, so that is X dot Y whole bar. So simply you can observe, that is X dot Y whole bar, means that is one of the NAND gate. So we are going to apply the X and Y, that is A bar and B bar, as inputs for the OR gate implementation using NAND gate. So I have the two input terms as A bar B bar. So already we have saw the inverter. So first one is that only. So this is the third one. So we have saw already inverter. So inverter means the same input makes that inversion. So we have to make two NAND gates. So I have connected with two NAND gates with the two input gates for the final NAND gate. So finally we are getting A plus B. So this is the final input. So remember or by heart this one. We have to take two A bar and B bar, two inputs to the final AND gate, so that we can able to get the final A plus B OR gate. So if you know this the final equation or the final circuit one, so you can know how to take A bar and B bar. So that is the simple inverse of the NAND gate, or the simple same input for the two NAND gates. So that makes inversion. The inverted outputs take as input, that makes the final output ABB. As I said before only, whatever may be the circuit inside, how many may be the NAND gates inside, so the same logic can be produced or not, we have to check like that. OR gate, that is A and B is coming, A plus B is going out as output. So in our implementation also, A and B is coming, so A plus B is going out as output. So this is the required one. We are going to find that only. With the help of three NAND gates, we are going to see the final output as A plus B. So the required one is this. So remember, we have to have three NAND gates for the implementation of OR gate with the help of NAND gate. Up to now we have discussed NAND gate implementation for the three basic gates. So now NAND gate can be implemented for the other universal gate as well. So we are going to see that only. The NOR gate can be implemented using the NAND gate. I think already we have saw up to now, that is OR gate. So NOR means what? Just the OR plus NOT. So that's it. Can be simply obtained. So for at this previous one, we have saw already the OR gate. So by adding NOT, that becomes NOR. So we have already saw the NOT also, the inverter gate at the first only. So we are going to just merge those two only. So that's the final circuit. So let's see that one. So we know the truth, OR plus NOT is equals to NOR. The formula is also represented on the lines itself, that is A plus B, and inversion, that is A plus B whole bar. We are going to see that A plus B whole bar can be implemented with NAND gate or not. So first three gates, that is A and B are inversion, that is A bar B bar. So we are getting A plus B. Just add NOT gate, that gives our A plus B whole bar. So I think we know how to implement OR gate and NOT gate. So we have saw both of the implementations before itself. So just add those two, we are going to get final output, that is NOR gate implementation. So this is one of the universal gate other than NAND gate. So you can also see the highlighted box represents the same thing, the logic. AB is coming, A plus B whole bar is going out. So with the help of only NAND gates, we are doing that. So that is universal gate. The universal gate also done, that is the NOR gate. So we have done the basic gates, the NOR gate, and the two gates are remaining. So these two gates are very important. So the first one is XOR gate and second one is XNOR gate. So if you know the XOR gate, that's it, it's completed, because the exactly opposite, or if you invert the output of XOR, that is becomes XNOR. So XOR is very important. So let's start with the XOR gate implementation using NAND gate. So let's take some formulas already we have discussed before, that is for the NAND gate and A dot B whole bar for NAND gate, and that is A XOR B for the XOR gate. So XOR can be simply written as A bar B plus A B bar. So if you don't know why this got, so this is the standard basic formula. So the circuit for this is shown in the next picture. So if you want more details that why this is this even gate, so because this is a circuit equation, why even minimizing and showing with the simple symbol, because if you want this is a regular use, so we will be going to use this XOR gate very often, very usage. This has many usages. So that is the reason we are going to use this very regularly. If you want more details, you can check out the classification video that I am giving in the description box. So by seeing that, you can able to observe, or in the logic gates video, you can be clarified, very clarified with the XOR and XNOR gate as well, with the truth tables also. If you backtrace the formula, that is A bar B and A B bar, you're going to get this circuit. So this has already been discussed in the previous video. So let's check out that video, that is logic gates video. So with this circuit, we are going to make the first circuit of our using NAND gates. With the help of NAND gates, we are going to build with the XOR gate. At first, by seeing this, you might be confused. So don't be confused. It is very simple. How? So we have see all the circuits or all the implementations of NAND gate, or the circuit element present over there. So we have already saw the implementation of NAND gate for the NOT gate, the inverter, and the next one is AND gate. So we have already saw the AND gate implementation for the NAND. So the next one is OR also we saw. So these three are the basic gates. So we can implement the basic gates by using the NAND gate. So simply replace all the gates with the NAND gates. So the first NOT gate is replaced as by passing those same input. So I think first two are you understood, I think so. So the next NAND gate, so in the same line. So observe as two lines. So the first one is continuous line, the second one is continuous line. In the second line, the second and third NAND gates are the same. So that belongs to AND gate. So we have already saw AND gate. So that's why I wrote like that. So the fourth one and fourth one we will see. So in the second line also, the first one is NOT gate and second two are belongs to AND gate. So that the final three belongs to OR gate. So we have already saw in the OR gate we have to have inverters. So A bar, B bar. So we are going to have A plus B. So the inverter means, so we are going to have the inversion circuit. So the same thing as OR gate only. We have to observe the OR gate once again. Now it's clear for you, I think so. So this is the highlighted way that I am showing you, so that you can able to understand what gates I am changed with corresponding to the basic gates and NAND gate I have changed. This is the big circuit first thing. So at first sight we can see it is a big circuit. So if you see the third and fourth NAND gates, those are simply nothing but two NOT gates, two inverters. So what is the use of two inverters? Assume that you first inverted, then again inverted. So again we are going to get same now. So first you are going to have, suppose if you have 0, flip 1, flip 0. So two flips makes you again the same thing. So we are going to discard those 4 NAND gates because two flips makes the same thing. So no change. So we are going to have discard those 4 NAND gates. After discarding those 4 NAND gates, so this is the final circuit that you are seeing. So try to remember this one, or try to exactly replace all and try to find out by your own. So this is a simple thing. I think you can able to understand by discarding. This is the final circuit. And one more important thing that I forgot to mention is this circuit after discarding those 4. So this is the minimized one. So this uses 5 NAND gates to represent the XOR gate. Remember these 5. So we are going to see the another implementation. So this is the first one. So first implementation. So in the first implementation, we just used 5 NAND gates. So up to now we have saw the gates and the output equations. So let's have some Boolean equations as well. We have saw the 2 inputs makes the final output. The final output you can observe those final equations. This is the final equation, that is a bar dot b whole bar, and the second input is a dot b whole bar. So if you apply the NAND gate, we are going to get our required one, that is XOR operation. So let's solve this one to get the final output as XOR operation. A XOR B. So if you observe that if you take it as A and B, so just simply A dot B whole bar. So just simply I have put that only. So the first expression dot second expression whole bar. So don't simplify first itself. So in the second step, so we are going to expand by using Boolean expression. So I think you know the Boolean function or Boolean formula. So dot is converted to plus, plus is converted to dot. So here dot is there, convert to plus, and bracket is, the upper bracket, upper one has to be divided. Upper bar has to be divided for both of them. So again 2 bars are there. 2 bars can be cancelled to get the final output as a bar dot b plus a dot b bar. So this is the final output equation of the required thing, XOR operation. Yes, I hope you understood that. So it's time to discuss the XOR only, but the second one. So in this, we are only involving the NAND gate, and we have only the 4 gates. We have only the 4 gates of NAND, so can be implemented for the use of XOR gate. So let's see how to implement with the help of only 4 gates. We have already saw with the help of 5 gates. So now let's start. This is big circuit. I don't understand this. So how can I understand? So let's wait. So can I say it simple trick for remember this circuit? So yeah, I will say this simple trick. So listen carefully. So if you want any circuit for the XOR operation, so using 4 NAND gates, so just know the inputs of the last NAND gate. So the input for the last NAND gate that we are applying is a dot b bar whole bar for that. So the second input is a dot b whole bar, and again whole bar for that. As you seeing there, you think that this is a big equations I cannot remember. So if I show you the final thing, how these formulas are from the equation of the XOR gate, so then you can able to simplify that. So you can able to observe that's very simple one to understand. So let's start or understand how that came, how that inputs has to be applied to the final NAND gate. So if you want to know how to apply that, so you have the formula, that is a bar dot b plus a dot b whole bar. So just to take 2 bars, so 1 bar above that whole equation and again the output equation, and the second bar above that whole lower bar, and you can able to find this output, this equation, that input equation, so that you can able to split by with the help of the Boolean equation or Boolean expression. By splitting I can so you can also observe the first output equation can be splitted with a plus, and a bars are also splitted. So in the next expression, so we are going to just cut off those 2 brackets or 2 bars. So in the next expression, we are just going to divide the inner brackets with the bar. For the Boolean expression, we know Boolean expression. So dot is converted to plus, plus is converted to dot, and the bars are splitted. So this is the next step I have done. So the next step is to multiply the a and b to the inside brackets. So after multiplying, we are getting 4 terms. I hope you know the Boolean simple things. That is, so don't worry. I'll also show you in the next one, in the upcoming video. But see how the output equation is coming from the equation that we have applied to the input equations. So these are the things that has to be known in the Boolean algebra, the simple things. So let's see that things. So a dot a bar and b dot b bar is 0. Why? So if you have 0 into 1, that is 0 only. So if you have 1, so 1 into 0, that is again 0 only. So if you take the bar again and again, so in the one term you are going to have 0. So that makes the whole thing as 0. So if you add anything, that is a plus 1 or b plus 1, you are going to get only 1. So if you have same digit, that is a, so if you have 0 plus 0, you are going to get 0. 1 plus 1, you are going to get 1. And again b plus b also gives rise to b. So these are the things that in Boolean algebra. So the first one is applied in that equation only, so that we are going to discard those a plus a bar and b plus b bar. Those are zeros. So discard those two and you are going to get final output of the middle two terms, that is a bar b and a b bar. So this is the output of XOR equation. So XOR is completed. So let's see the XNOR also. XNOR is just the NOT is added, that's it. So we have to add NOT gate after the XOR gate. If you trace back the final equation of the XNOR gate, so that is a bar dot b bar plus ab. So if you trace back that, you can able to observe this is the final circuit equation. So don't worry, this circuit is not we are not going to replace these things to get the final. So we are just going to add NOT gate so that we can able to observe the XNOR gate equation as well. Same thing. So in the XNOR also we have two types of implementations. There might be any kind of implementations, but in this video we are going to see with the help of only two implementations, two types of circuits we can able to make with the help of only NAND gate. So inputs are same, A and B. Output is the final equation, that is XNOR equation. So that is the thing that we are trying to find or trying to make. So whatever may be the inside circuit, how many maybe the NAND gates we have used in inside circuit, so the inputs and output has to be same, so that makes sense. So we can see the first implementation. So in the first implementation we have the same circuit that has in the XOR gate, so just we have added the NOT gate, so that becomes the XNOR implementation. So in this we have used 5 NAND gates or the implementation of XNOR gate. I have highlighted there. I think you can able to observe. So first one is XOR, second one is NOT gate, that makes XNOR gate. If you know XOR perfectly, the XNOR is very simple. So the first implementation is very simple if you know XOR very clearly. So let's see the second implementation of the XNOR gate as well. So this is the second implementation. So the second implementation can be obtained with the help of formula itself. So I think you know this formula. If you don't know, please refer to my video of logic gates. So let's start this with this equation. So if you observe the a bar b bar plus ab, so you have to add 2 bars. So after adding 2 bars, break the inner bar. So if you break the inner bar according to Boolean algebra, you are going to shuffle with the plus with dot, and bracket has to be separated. So after distributing, you are going to get that. So that equation only our final equation. So that has to be implemented with the help of NAND gates. So if you observe clearly, you can able to see there 3 NAND gates. So the first NAND gate is 2 inputs. That is, if you observe a bar b bar, so you assume that x dot y whole bar, that is one NAND gate. So that is for 1. I have highlighted with the red highlighted, that is 1. So that is 1 means 1 NAND gate. So the second NAND gate is a dot b whole bar, that is second one. And the third one is the highlighted with the box. So that is a dot b, means that the first expression dot second expression whole bar. So that is the final one. So again in the first one we are having bars. So bars means the same output produced in the NAND gate. So that is 2 bars means 2 NAND gates. So yeah, for the inversion we want 2 NAND gates. So total 5 NAND gates we are going to use for the second representation. So let's see how to represent that. So don't be confused, just start with the a bar dot b bar. So I have took 2 not inverter gates. So ignore up to some time ignore the top NAND gate. So consider the bottom 2 NAND gates. Here you are getting outputs as a bar b bar. So after that I am taking another NAND gate for mixing of a bar and b bar. So after mixing that I am getting a bar dot b bar whole bar. So now we are considering the top one also. Take inputs as a b, so you are going to get output as a dot b whole bar. So just apply these to a NAND gate. So that's it, that is our final output. This also we are going to implement with the help of 5 NAND gates. If you just simplify that, a bar dot b bar whole bar dot a dot b whole bar for the full equation. So if we solve that, we are going to get a XNOR b, or a bar b bar plus ab. Thanks for watching up to now.